Platform engineering. What is it? Is it just running compute, networking, and data, or is there more to it than that? Is it DevOps or something else? The answer is yes and more. Platform engineering is a new way of thinking about software delivery. It's related to DevOps, yet it takes those ideas even further. Platform engineering is an evolution of the way software is developed and delivered. In this video, I'll introduce you to the ideas behind platform engineering. I'll talk about internal developer platforms and how they can simplify the complexities that developers deal with every day. By the end of the video, you'll have a solid grounding in how platform engineering can reclaim lost delivery velocity and re-energize your DevOps practices. I'm excited about the potential for platform engineering, as I believe it's the next logical step in software delivery. We've got a lot to cover, and I can't wait to get started. So let's dive in. What is platform engineering? When I first heard the term platform engineering, I took it literally. I thought it simply meant engineering of platforms, as in all the platforms involved in running applications. That's not wrong, but it doesn't tell the whole story. Platform engineering is relatively new, yet it has gained quite a lot of traction in the industry in a short time. Gartner claims that 80% of large engineering organizations will establish platform engineering teams by 2026. So what's so compelling about platform engineering? Let's break it down. I like to define terms when starting with a new concept. So let's start with platform. Webster's dictionary has a definition that provides a good start. An application or website that serves as a base from which a service is provided. This is close to the definition of platform that's most relevant. Platform engineering encompasses all kinds of applications that provide services, both business-focused applications that provide business services and applications that support the software delivery lifecycle itself. For our purposes, let's refine the term platform a little. A platform is a system on which applications are built. So platforms are the foundational building blocks of applications. They're designed to be extensible to support any application that could be built. Generally speaking, there are several types of platforms. Everything starts with hardware platforms. The physical processors, memory, data storage, and networking hardware are the foundation of all computing. Further up the stack, so to speak, we have software platforms, operating systems, hypervisors for virtuousness, and container orchestrators provide runtime platforms. Above that, we have all the platforms needed to develop, deliver, and operate software. Version control systems for developers to version their code, CI/CD platforms to deliver the code to production environments, and observation platforms for logging and telemetry visualization. Just to name a few. Each of these systems are complex platforms unto themselves. They're designed to be extensible and configurable to operate and deliver any conceivable application. So is the engineering part of platform engineering all the work that goes into building, configuring, and using all those platforms I just mentioned? Yes and no. Platform engineering teams do support all these application runtime and software delivery platforms. That's the work of provisioning, configuring, and maintaining the platforms themselves. However, that's only about half the job. The other half of platform engineering is the development and support of a particular independent purpose-built platform, the internal developer platform, or IDP. Throughout this course, I'll be focusing a lot on that job, the work providing a bespoke developer platform specifically for internal developers. I'll explain why the industry is moving in the direction of platform engineering, what an IDP is and how to build one, and we'll talk about the skills necessary to work on a platform engineering team. We've got a lot to cover, so let's dig in. The purpose of platform engineering. Let's take a few minutes to understand the purpose and goals of platform engineering. Industry movements such as this one don't spring out of nowhere. They have a purpose. What's the purpose of platform engineering? What problem is it designed to solve? To understand that, let's consider the state-of-the-art in software delivery practices, DevOps. DevOps and its related practices like site reliability engineering are at least 10 years old. At that time, when DevOps was gaining traction in the industry, the act of pushing to production was much simpler. It required some knowledge of a version control system and perhaps a CI/CD tool, like Jenkins. Developers were able to pick up these few tools without too much fuss, and were then able to take on some of the traditional ops responsibility as good DevOps practitioners. What's changed since those days? Today, the landscape for it teams across DevOps and all other stakeholders is orders of magnitude more complex than it was just 10 years ago. CI/CD platforms, observability, security logging, secrets management, container orchestration, artifact repositories, cloud platforms, the list goes on. Each one of these tools are entire platforms unto themselves. Over time, more and more of the burden of all that complexity shifted to developers. What was once a relatively simple job, write code and push it to production, became far too complex for developers to manage on their own. Developers operating under the you build it, you run it paradigm spend increasingly less time writing the code and much more time on deployment, testing, anything but writing code. They're no longer just developers, they're DevOps, SRE, and everything else. Each of the tools involved in the software delivery process require considerable time to understand, configure, and support. This trend turned the sharing of responsibilities between dev and ops into a velocity killer. So platform engineering can be considered an evolution of DevOps. It doesn't replace DevOps, and it's not an alternative to DevOps. It's more like an enhancement or an upgrade. Platform engineering exists to provide a service to developers in the form of an internal developer platform. The IDP provides an abstraction between developers and the complexity of modern software delivery platforms. It reduces the surface area of their concerns so they can focus back on writing the applications that add business value. Internal developer platforms do this by exposing a curated set of self-service capabilities to developers built on proven patterns. Platform engineering versus DevOps and SRE. It's important to have a clear perspective on platform engineering before we try to make it work. So let's spend some time on how it relates to other practices. As I've mentioned previously, platform engineering is an enhancement of DevOps, not a replacement. DevOps still has plenty of important applications to modern software delivery. Its principles of shift left, small batch sizes, and continuous improvement are no less relevant than they were 10 years ago. These principles are not in conflict with platform engineering. On the contrary, they are critical to the work of the platform engineering team. The IDP should be developed as a product, and we should apply DevOps principles and practices to it as we would any other. Platform engineering lives in the space between developers and operators and defines a new specialty, the platform engineer. Platform engineers are the builders and maintainers of the IDP. They're also directly involved in the engineering and support of the software delivery platforms the IDP abstracts. The skills involved in platform engineering are very similar to another modern software delivery practice, site reliability engineering. When site reliability engineering was originally developed at Google, the first SREs were operations staff with experience in software development, and software engineers with an interest in systems administration. SRE applies software engineering skills to task automation and systems operation. Platform engineers need a similar hybrid skills. An IDP is an automation platform. It integrates with software delivery platforms into a sort of aggregate super platform, acting as a proxy for software delivery and compute platforms. Building an IDP requires software engineering skills and experience to design and develop its developer-facing components. Platform engineers must also understand how to implement and support the software delivery and infrastructure platforms, from version control systems to CI/CD systems to container orchestrators. They then integrate, via APIs, these platforms with the IDP. Over time, the responsibilities of the developer have blurred into DevOps engineer, release manager, security tester, and more. With the introduction of platform engineering, developers have a clearly defined contract that determines precisely how they interact with the software delivery process. There's a clear line that defines the end of their responsibility. On the other side of that line is the scope of the platform engineer role. Developers still participate in some operations-level work, in collaboration with the platform engineering and operations, by contributing to the design and function of the IDP. The platform engineering team is responsible for the IDP and the delivery platform it abstracts. The complexity of the software delivery process is simplified, relieving developers of responsibility outside their scope. Operators or systems administrators are responsible for the lower-level platforms, such as identity management, operating systems, networking, and virtuousness platforms. This new clear delineation of roles and responsibilities frees developers to focus on their primary job of writing and testing application code. A dedicated platform engineering team has the time and resources to focus on the complexities of building and supporting a custom-built platform specifically for their customers, the developers. There's way more to talk about with platform engineering, so let's move on. Benefits of platform engineering. Platform engineering has a broad value proposition spanning roles and personas across all stakeholders in software delivery. Having said that, implementing platform engineering is not a trivial task. It requires significant investment in time, money, and human resources. Let's run down the list of primary benefits so we can understand why it's worth the effort. IT organizations that adopted DevOps saw improved delivery velocity. Over time, they found their delivery velocity degrading as their developers were stretched ever thinner across the expanding platform landscape. Platform engineering offers an opportunity to regain this lost velocity, which translates directly into higher ROI in development efforts. There is an important human element here as well. It goes without saying that overworked, burnt-out developers are not productive. Burnout leads to lower morale and higher turnover. Redistributing the work of software delivery leads to more effective, productive teams. While every stakeholder in the software delivery process will appreciate higher velocity, executive leadership and the developer teams will be most interested in this benefit from platform engineering. Greenfield development efforts often begin with an app dev team starting from scratch. Design choices must be made and remade with each new product. Which language, set of libraries, which database will you use? What are the best options based on the requirements? These decisions must be made before the developers can write a single line of code. Once they're finally settled, the team must then spend time requesting the provisioning of new environments. In some cases, an enterprise architecture team may have created a set of reference architectures to provide a starting point for new applications. This is a good thing, but it's just documentation. not really something a team can pick up and execute. Platform engineering uses the concept of golden paths to establish reusable patterns for building and deploying new applications. These are not just decision tree graphs or descriptions of approved components. They're deployable packages of application and infrastructure code. Development teams can request new instances of an application template through the self-service features of an IDP and be up and running with a deployed starter application in minutes. We'll talk a lot more about golden paths throughout this video. Application development, enterprise architecture, product management, and compliance teams will appreciate the standardization offered by platform engineering. Managing infrastructure, whether on-prem, in the cloud, or both, is a challenge. Medium to large-size enterprises often have difficulty keeping track of the relationship between applications and the infrastructure on which they run. Configuration management databases are typically used to maintain those relationships. Maintaining the configuration data can be a time-consuming and resource-intensive process, often requiring manual data entry. An IDP can be made to serve as the single source of truth for both application and configuration data. An IDP handles both application definition and deployment, so it maintains a link between the application record and all dependent infrastructure. IT operations and finance teams can use reports built on that data to gain insight into infrastructure spend and use that to plan and budget for future infrastructure needs. Most IT organizations require some level of governance to manage risk and compliance. Regulated industries especially need IT governance to maintain industry certifications for quality management and security. This is another area where platform engineering can help. The platform engineering team can collaborate with development teams to set standards for how common application features should be implemented. Security-sensitive features such as user identity, application logins, service accounts, and secrets can be standardized. All these and more can be built directly into the application templates provided to developers through the IDP. This baseline ensures that new applications start off with best practices implemented from the first deployment. Software components of applications have life cycles. Examples include application runtimes, like Java and .NET, open source and commercial libraries, databases, and messaging systems. Each of these components has an end-of-life date, past which the developer or vendor will no longer support an older version. There's also the problem of security vulnerabilities. New vulnerabilities are discovered all the time. In either case, IT organizations are constantly having to replace old versions with new, and insecure versions with patched versions. This is a major challenge when there is no record linking applications with their components. Upgrading and replacing components requires hours or days of discovery just to find them in the environments. Once again, an IDP can help. If all applications are built on common templates and there is a record of all deployments, then it is simple to develop a component up report. Security and compliance teams can ask for applications that contain a particular component and work with development teams on a remediation plan for any lifecycle or security issues that may arise. So platform engineering provides benefits across an IT organization. All the stakeholders of software delivery can develop new capabilities to enhance their part of the delivery lifecycle. The goal is to design just enough of the MVP to have a clear backlog of tasks to tackle. Benefits of internal developer platforms. Platform engineering offers an approach to reclaiming lost velocity by supporting developers with an internal developer platform. Let's dive into how an IDP simplifies the job of developers. As a quick content note going forward, I'll use the terms internal developer platform, IDP, and developer platform interchangeably. The most important function of a developer platform is to simplify developers' interactions with all the tools, apps, and platforms that enable software delivery. Each of these systems has a similar job: to automate and simplify a part of the software delivery process. Let's take Jenkins as an example. The scope of a CI/CD system like Jenkins is to automate some of the tasks involved with delivering software, such as testing, compiling, and deploying. Instead of having to script each of these steps by hand, developers and operators can create a single Jenkins pipeline that includes all of these steps. The pipeline is an abstraction that encapsulates those steps into a single simple workflow representation. This is one example of how an individual software delivery platform makes life easier for developers within a limited scope. Jenkins is just one of hundreds of tools available to enable software delivery. Here's a short list of the other types of platforms that can be enabled through an IDP. Compute and container orchestration, continuous integration and version control, continuous deployment, databases, monitoring, and security. We can get a glimpse here of the complexity involved in software delivery, and this isn't even a complete list. You may have noticed that not all of these are necessarily delivery platforms. Compute and database platforms are included as well. Platform engineering includes both platforms that support software delivery and the runtime platforms that make up application infrastructure. With all this complexity, developers need a new abstraction layer, not just over the individual aspects of software delivery, but across the entire ecosystem of tools and platforms. A developer platform wraps a set of tools and interfaces around software delivery platforms. These platforms are independent of each other, yet tied together and exposed to developers through the developer platform. For the purposes of this video, I'll be referring to these as component platforms. So the goal of the developer platform is to reduce the surface area of each component platform to a limited set of options that represent the best practices. Developers can then make a few choices when setting up a new workload, rather than tens or hundreds. Well-designed developer platforms strike a balance between the set of sane defaults for each component platform, plus advanced configurations to take more granular control when necessary. Large enterprises often have hundreds, sometimes thousands of applications spanning a huge infrastructure. Managing the records of these applications can be quite a challenge. Enterprise architects and those in similar roles must spend a lot of time record-keeping in dedicated systems like configuration management databases and enterprise architecture management systems. Using a developer platform as the source of truth for application configuration and inventory can greatly simplify this work. If all new applications must be registered with a developer platform in order to be configured and deployed, then that IDP can maintain records of all applications, their configuration, and their infrastructure. IDPs can be integrated with CMDB and EAMS systems, pushing applications records into them as new applications are created and their supporting infrastructure is deployed. Thus, those management systems become component platforms alongside delivery and infrastructure platforms. So independent developer platforms enable developers by reducing their concerns for the mechanics of application configuration and deployment. This reduces toil and burnout. There are more great benefits of platform engineering, so let's keep going. Golden paths. Software systems are complex. They consist of many parts such as runtimes, libraries, and binaries. These atomic components are combined to create software, front-end user interfaces, and back-end APIs, for example. Then there's the platform ecosystem surrounding the software delivery process, and non-functional concerns like logging and observability. Each one of these verticals have many configuration options. Taken together, there is a near infinite set of possible combinations, even in relatively simple systems. It's no wonder developers are overwhelmed when every project starts with this jungle of choices to be made. There's a better way. Golden paths can be used to design and build a library of pre-built components from which to assemble new applications and systems. The concept of golden paths isn't new. When I was an enterprise architect, we referred to them as paved roads. They are also known as application patterns and reference architectures. All these concepts share a common thread. Rather than starting from scratch every time, why not build from proven parts? There's a strong manufacturing metaphor here. For example, major automakers are car designers and assemblers, not car fabricators. More than 50 of any given new car is made from parts provided to the automaker by an outside vendor. Automakers focus their attention on vehicle design and assembly, and leave the intricacies of wiring harnesses, transmissions, entertainment systems, and suspensions to specialized vendors. This leads to cost savings and efficiency in the manufacturing process. That same concept can and has been applied to software delivery. In fact, DevOps has deep roots in lean concepts that originated in auto manufacturing. Platform engineering is designed to rationalize software delivery across these same lines. Developers should not be loaded up with every conceivable aspect of development and delivery. The platform engineering team builds and supports an internal developer platform. The developer platform takes ideas like reference architectures and makes them more than just reference. They're executable. Using modern techniques like infrastructure as code, these patterns can be built as deployable components. The resulting developer experience becomes like a modern factory floor. Instead of having to fabricate every part from scratch with a welder and a block of raw steel, developers pull pre-built parts from marked bins. In this metaphor, these parts are templates based on golden paths. Using templates allows developers to work far more efficiently, with less effort wasted on the dead ends of prototyping and proofs of concept. Using the components provided by the internal developer platform, the concepts are already proven. Delivery velocity is just one of several benefits of the platform engineering approach. We've discussed the benefits of standardization as well. If we look at the code of any given application, we can see that a good portion is non-functional. That doesn't mean unimportant. It's critical to the overall function of the application, but it's not directly related to the purpose of the application. Examples include logging libraries, security components, like authentication and authorization, specialized math libraries, network communications, and database connectors. All of these components are necessary for an application to do its work, but they're not the actual calculations and data processing that go into an e-commerce, accounting, or customer support system. So all these non-functional elements are needed by most applications, but they're not value-added. The role of the platform engineering team is to identify all these common components and then design and build reusable, configurable, modular implementations of them. These modules are then used as the foundation for application-level components that are provided through an internal developer platform. Developers use the IDP as their virtual parts bin, confident that anything they build from those parts will incorporate all the best practices in software design. They can then focus on adding the functional parts that automate business processes. Using golden paths implemented as modular application components, developers can work efficiently rather than having to reinvent the wheel with each new effort. Stakeholders across IT and the business can rely on the software delivery process to produce reliable, secure applications. Platform engineering patterns and antipatterns. Platform engineering is a methodology like DevOps, site reliability engineering, Agile, and many others that have come our way over the last 20 years. You're probably asking, is platform engineering just a new fad or does it have something to offer? Will it work if I try it? There's an old saying. We learn more from failure than success. Let's apply that to platform engineering adoption. Drawing from personal experience, I've seen a common thread among less successful transformation: a lack of internal communication and alignment. DevOps, Agile, platform engineering, all these methods and techniques have something to offer if everyone can agree on the how and why. Without consensus on the reasons and methods, any implementation is doomed to failure. A common failure pattern is misaligned expectations stemming from a misunderstanding of the methodology itself. Organizations should adapt the principles of any methodology to make sense for their context. As long as everyone within an organization agrees on how to adapt, an implementation has a good chance of adding value. So let's dig into some common antipatterns for platform engineering adoption based on its core principles. Using the platform engineering team to dictate what tools developers will use by gatekeeping through the developer platform is a platform engineering antipattern to be avoided. Platform engineering is not a governance team. Platform engineering exists to serve developers, not the other way around. In practice, that means building the developer platform around the tools and platforms your developers are currently using. Even technology that may be nearing containment or obsolescence must be supported if it's already widely used. It may seem counterintuitive, but if your developer platform covers all the technology that is in use, that will make sunsetting old technology easier. Build a developer platform that supports the way your developers work today, and it will support them in managing technical debt and technology life cycles going forward. Having said all this, platform engineering can and should work with governance and compliance teams to bake patterns and best practices into golden paths. Include standards for secure coding and coding conventions for readability and application templates, so your developers can use them over and over without having to reinvent them with every new product. Platform engineering concentrates a set of skills into a dedicated team. This may seem like the battle days pre-DevOps, where skills and people were siloed. Without proper execution, a platform engineering team can become just another silo, and that's an antipattern. The most important aspect of platform engineering as a practice is self-service. I'm not here to be a platform engineering purist, but I will go out on a limb and say, platform engineering without developer self-service is just sparkling DevOps. Jokes aside, developers must be able to create new dev environments on demand in minutes. This is what makes platform engineering an enabler instead of a bottleneck. A platform engineering team cannot be a team of one. That's an antipattern and an oxymoron. It's appropriate to have one or two developers do research and prototyping with an internal developer platform, then report back to the larger organization with findings. A full implementation of platform engineering must involve senior leadership, as a green light will require real investment. A new team will need to be created to support the initiative, and their charter must be platform engineering and nothing else. Those were some of the key antipatterns and failure modes, the dawns of a platform engineering initiative. Here are some of the DOS. Do have the platform engineering team collaborate with application development teams on the internal developer platform throughout its development from concept through delivery. Do build the internal developer platform around the tools and technologies your developers use today, without exception. If it's in production, it's supported. Sunsetting obsolete technology is a separate concern. Do develop the internal developer platform as a product, like any you would sell to an external paying customer. In conclusion, platform engineering has a lot to offer any organization that can agree how to adapt it to add value. This consensus can be built through internal conversation, healthy debate, and a focus on outcomes. Do I need platform engineering? I've spoken generally about the promise and benefits of platform engineering, but how can you know if it's right for your company? Here's a simple way to answer the question: do you need a developer platform? This may seem like an oversimplification, but at the end of the day, it really does come down to that. You can break it down a little further by digging into the features of a developer platform. Do we need self-service? Is our platform ecosystem complex enough yet to benefit from golden paths? These are the right questions to get to the heart of the question, do I need platform engineering? We can also use a few metrics that correlate with the need for platform engineering, the size of your organization, and the complexity of your platform ecosystem. It stands to reason that the larger and more complex your organization, the more likely you will benefit from an IDP and a dedicated platform engineering team. There are no fixed numbers for these metrics, but we can approximate. Any developer organization with 75 to 100 developers or more is likely to benefit from an IDP, even if that organization has a relatively simple platform ecosystem for software delivery. The infrastructure self-service and golden path features should improve key delivery metrics. Of course, the larger an organization gets, the more component platforms it's likely to use. Very large organizations that have grown organically over time often have a broad, highly heterogeneous platform ecosystem. This may be the single strongest case for a platform engineering team and IDP. Ecosystem complexity has an outsized impact on delivery metrics and developer burnout. So it's clear that very small organizations with simple ecosystems are on the low end, and large organizations with complex ecosystems are on the high end. What about the middle? In those cases, growth trajectory is a good metric to use. If you're working in a fast-growing organization that's adding new component platforms, you should consider planning for a platform engineering team. Keep in mind that org size and platform complexity are indirect indicators of the most important metrics of all, software delivery. Platform engineering is a means to an end, and that end is high delivery velocity, with low rates of deployment failure, and high production stability and reliability. The goal of platform engineering is to improve the classic DevOps metrics, lead time for changes, change failure rate, and mean time to recovery. So the first question is, are you measuring these metrics? If not, start there. If these metrics are all in an acceptable range, you may not yet need a developer platform. The next question is, are you really measuring these metrics? I don't mean to be cheeky here, I've done many DevOps workshops. One of the common challenges I've seen is that measuring these metrics accurately can be tricky. Measuring change lead time is especially difficult. It's very easy to miss steps when work's behind the process. I've seen teams initially report lead time in hours, then realize through discussion that it's actually days when you add up all the critical path testing and validation steps. Take care to measure honestly and accurately, and you'll be in a much better position to make improvements. Automating the measurements of metrics, such as lead time, can be very helpful. Many open source and commercial CI/CD tools offer time stapling features that can be used to correlate changes with deployment times. These data can be used to track changes from a task on a backlog all the way to a production deployment. So ask yourself and your peers honestly, do we need platform engineering? Using these metrics and questions, you can be confident in your answer. If the answer's yes, you'll have the data to support your argument to colleagues and leadership. Making the case for platform engineering. You've done your homework. You've read up on platform engineering, and you understand what an internal developer platform can do. You've checked in with your team, and you all agree it's the right time to start up a platform engineering practice and IDP. What now? Now, it's time to make the case to the rest of your organization that a platform engineering team will be worth the investment. The task at this point is to educate yourself, your team, and your organization at large. Educate all stakeholders in the general value proposition of platform engineering so they can understand how it will add value specifically to their jobs. Once you've demonstrated that you can make a case for executive sponsorship, in many ways this process is not much different from the original DevOps initiatives of the last decade. The key difference is the scale of the investment. DevOps transformation tend to involve training and tooling. While not trivial, these are limited scope investments. It's not very difficult to make the case for some tools like a version control system and CI/CD and fund a few DevOps workshops. Platform engineering, on the other hand, is a significant investment and dedicated headcount over the long term. The justifications and projected return on investment must be robust. The scale of the problem must match the level of investment needed. The best way to demonstrate that is through hard numbers and objective metrics. So the first steps towards a platform engineering practice is research and data gathering. Here are some key tactics for making your case. First, start with objective metrics. Demonstrate that your DevOps metrics are not where they should be. If you don't have these metrics, start there. Start a project to measure these metrics and business stakeholder sentiment around IT services. If you can show that delivery velocity is unacceptable and the business is feeling that pain, then you have a strong case for investment to solve the problem. The next step is to research the current state of your organization. Developer time is precious and expensive. If you can show that it's being wasted, you may be able to get support for an improvement initiative. Time tracking is tricky and a time sink unto itself, so it may not be the best way to measure waste. Developer interviews may be more effective. Interview developers about their experience in developing and deploying software in the current state using the platform ecosystem available to them. Design a survey to measure how much time developers spend doing their primary jobs versus the extra toil involved in deployment. Finally, use your findings to express ROI in terms of STA equivalents. Use data from the Developer Experience Survey to estimate how many hours are being wasted per developer across your entire organization. For example, if 100 developers are spending 20 hours a month each on deployment toil, that's 20 hours a month of waste. On an annual basis, that's the equivalent of almost 12 full-time employees. That's at least 2 entire Agile development teams, including product managers. So making the case for a platform engineering team is really a project unto itself. You'll want education, objective metrics, a clear ROI statement, and a draft implementation plan. If you put in the work to gather this information and present a compelling argument, you should have a solid shot at getting the investment for a new platform engineering practice. Starting a platform engineering practice. At this point in our journey, we've made the case for a platform engineering practice, and everyone agrees a developer platform will be valuable to application developers. We've got funding, now what? To start an internal platform engineering practice, we need to make decisions about problem statements, which problems are we going to solve, and in what order. Solutions, how will our internal developer platform solve the problems we identified? And measuring success, how do we know if we've improved? If you're familiar with DevOps and SRE, you'll see a lot of overlap here. The metrics used in DevOps to measure performance are among the same ones that should be improved by platform engineering. Let's look at each of these decisions. Platform engineering exists to solve problems regarding software delivery. However, be faster at software delivery is a bit too hand-wavy and vague. To start an effective practice, you'll want to be specific about the problems your team should prioritize. You need a clear set of marching orders with measurable results. These are some of the key DevOps metrics and the problems that may be associated with them. Lead time problems include things like, we don't know exactly how long our lead time is from one workload to the next, or changes to application X take too long to go to production. Regarding mean time to recover, things like, we don't have good telemetry, so it takes too long to detect failures, or production outages take too long to recover. And finally, change failure rate. It takes too long to correlate changes with failures, or too many changes lead to production outages. The first job of a platform engineering team is to build just enough of a developer platform to demonstrate the value it provides. This is known as a minimally viable product, or MVP. I'll use the term MVP throughout the video to refer to the very first beta versions of an IDP that are used by developers. There are plenty of metrics and potential problems to pick from, so it's important to keep the scope of work balanced and focused. For your MVP, don't try to identify a bunch of different metrics across many applications. That's too hard to measure. Select one or two high-impact metrics. This method will allow your team to focus on improving a small focused area of the software delivery lifecycle for a large impact across all workloads. The next step for the team is to determine specifically how their IDP will resolve these problems. Let's look to the metrics to see how an IDP can improve them. Lead time is the time it takes for changes to be deployed. The clock starts when a developer pulls a card or a task from a backlog and ends when the change is first deployed to production. A developer platform can shorten lead time simply by reducing the amount of code that must be written. Golden Path templates provide a foundation upon which developers can build new applications. Suppose that 20 of every application includes the non-functional code I talked about earlier. In that case, Golden Path templates can give developers up to a 30 head start on new applications. Golden Paths can also reduce test cycles. The templates are pre-tested as they're developed and then tested repeatedly during application testing. Test failures are therefore more likely to stem from application code rather than the template. Mean time to recovery is a measure of the speed of your recovery from a failure, which is the time between the identification of the failure and its resolution. This process is part observability, part development. Golden Path application templates include observability features out of the box. When new applications are deployed, an IDP can set up dashboards and logging syncs automatically. Once the failure is diagnosed, developing and deploying fixes should be faster using the IDP. Change failure is one of the most common causes of production outages. Using components based on Golden Paths can reduce the frequency of common bugs and mistakes. Templates reduce the amount of net new code in applications, reducing the surface area for defects. Identifying defects before they make it to production is the other half the battle. The developer platform can make it easier for developers and operators to run and view results for tests, thereby making it more likely for defects to be found and fixed in the test environments. Kaizen, or continuous improvement, is an important practice within DevOps. An IDP development effort is a perfect example of continuous improvement. We're finding problems, implementing solutions, and measuring the results. Measuring the outcomes from usage of an IDP takes time and patience. The MVP must first be rolled out and adopted by a few pilot teams and used for several workloads before taking new measurements. Some of the results will be objective. For example, an automated measure of lead time should provide a clear signal one way or the other. Other results will be more subjective. How does it feel to use the developer platform? Is it just another tool to learn, or is it actually reducing toil and tightening up the developer's workflow? All these objective and subjective results should feed into future iterations and improvements. Building a platform engineering team? So we've identified the problems, and we have a good idea how to build a developer platform to address them. Now we need a skilled, diverse team to build it. It's important to understand the distinction between products and projects. Projects have a limited scope, budget, and a definitive outcome. When a project ends, the team typically disbands to join other project teams as needed. Product teams, on the other hand, are responsible over the long term for a product that lives indefinitely. The team and the product are funded continuously for the full duration of the product lifetime. It would be quite difficult to build an IDP on a project basis. It is complex and must constantly evolve alongside the software delivery ecosystem. It's important for all stakeholders to think of the developer platform as an evergreen product, and for the platform engineering team staffing to be stable. Most importantly, everyone must agree that the platform engineering team exists primarily to serve the application development teams. Building a new team starts with identifying roles and responsibilities. Filling roles means identifying skill sets, then matching those skills to existing employees or new hires. Let's talk about the skills needed on a platform engineering team. For the most part, we can think of the team as an agile product development team. So we'll need 3 to 5 developers and a product manager that may double as an agile coach. Ideally, we also have one part-time solutions architect. The developers will need a variety of skills and experience. Some are more important than others. On the required side, back-end software engineering experience with deep knowledge of at least one developer stack, interest in developing an internal product versus an external customer-facing product. This is just as important as the skills, by the way. It's important that your candidates actually want to do this kind of work. Some experience with DevOps engineering, including CI/CD and GitOps. Bonuses include experience integrating systems with commercial products using APIs, systems administration, and command line interface development. If your IT organization already includes an SRE team, you may have a head start. SRE skill profiles correlate very well with the skills needed to build an internal developer platform. If you can spare a few SRE team members who are interested in building a developer platform, they'll make great founding members for your platform engineering team. Of course, it's not necessary to have SRE experience to join a platform engineering team. Anyone with the software engineering skills and an interest in the work can be a candidate. I also mentioned earlier that a part-time solutions architect is necessary. Developer platforms can become very complex, so if you have an architecture team with capacity, it's highly advisable to include them in the planning and design. As the team and developer platform grows, larger organizations may want to dedicate a full-time architect to provide consulting and oversight. The day-to-day operations of a platform engineering team should not be much different than any other agile product development team. One key difference, particularly at some organizations, will be the internal customer focus. It's safe to say that an internal customer model is not as common as a typical external customer model. The product manager should serve as the liaison between the platform engineering team and the rest of the organization, both the business and the IT organization. One exception to this rule is that the platform engineering developers will need to be in close communication with application developers. They'll need this to gather fast feedback on new features and bug fixes. A product manager may also handle requirements management, manage the backlog, and work with the platform engineering team to document releases and communicate them to the application developer teams. Software delivery platform engineering. Internal developer platforms are an important part of platform engineering, but there's more to it than that. A developer platform is a means to an end. The goal is to simplify the usage of many other systems. This requires deep knowledge and understanding of the complexity of the software delivery process and the tools that support it. Platform engineering teams should take a degree of ownership over all the component platforms behind the IDP. This doesn't mean that they should completely take over these systems. Operations teams still have a role to play in the day-to-day care and feeding at the infrastructure level. Operations maintains the systems, and platform engineering curates the developer experience. This includes software delivery systems like version control, container orchestration, continuous integration and delivery, and testing platforms. It also includes the infrastructure that would be provisioned by an IDP, such as compute, data, and networking resources. Platform engineers can approach their work from the developer's perspective. What is difficult and time-consuming about using these tools? Which features do developers interact with most often and which are less important? As a developer, what do I need to know about this tool to be effective? As a developer, what do I need to know about this tool to be effective? What can I safely ignore or only think about when necessary? These questions can help guide the work, both of building the developer platform and deciding exactly how to integrate software delivery tools with it. The platform engineering team should be involved in large-scale decisions about the software delivery ecosystem. When new tools are evaluated, they should have a seat at the table to help determine how easy or not it will be to integrate the new tool with the developer platform. Most commercial and open-source tools have well-documented APIs specifically for this purpose. So it's usually not a question of if, but how they can be integrated. It's important to plan integrations well in advance, both to make the integration successful and pave the way for developers to adopt new component platforms. Platform engineers have a unique perspective, especially in very large organizations, as they'll see many different patterns across lots of different workloads. This makes them well equipped to produce and maintain golden path templates. They'll see what works well and failure modes to be avoided. The actual development of templates is best shared between application developer teams and the platform engineering team. Both perspectives are important to balance the need for common patterns against the unique needs of particular workloads. So building an IDP is a major focus of platform engineering. However, software delivery platforms are at least as important. Both the IDP itself and the systems it integrates must have equal attention from platform engineers to fulfill their mission to make life easier for developers. Developer platform features and functions. Platform engineering is a service provided to developers in an organization. That service is the developer platform. A developer platform is a bespoke purpose-built system. It's used by developers to abstract away most of the mechanical details of software delivery beyond writing and testing code. One good way to envision the developer experience of a developer platform is to look at examples of other developer platforms. Hypercaselers like Google Cloud, IaaS, and Azure are not developer platforms per Southeast. However, supporting developers is an important part of their function. All of them provide multiple modes of interaction. A user interface in the form of a console, a command line interface, and APIs that can be used for automation. A developer platform is not a singular thing. It's a composite system designed to encompass and simplify developers' interaction with supporting systems relating to software delivery. The developer portal is the user interface of a developer platform. This is where developers can define new applications in their configuration, view existing applications, and deploy new environments. A command line interface is used by developers to interact with the services of the internal developer platform. This supports the typical repetitive inner loop of code, test, deploy. So developers have an option to interact with those features of the developer platform more efficiently than through the UI. Developer platforms can also expose APIs to support the user interface, command line interface, and any other automation use cases. For example, an API can support reporting on application configuration and status across all applications defined within the developer platform. The platform orchestrator is the component of a developer platform that reads an application configuration, then provisions and deploys it. This is largely driven by infrastructure as code. Let's move on and dig deeper into the inner workings of developer platforms so you can get to building your own. Developer platform architecture. Internal developer platforms are large, complex systems made of many parts. Internal developer platforms are large, complex systems made of many parts. In this video, I'll break down the major components of a developer platform and talk about how they work together to provide self-service and automation capabilities to developers. These are the components of the developer platform that developers interact with directly. The developer portal is used for large-scale application management and administration. An open-source example is Backstage, originally developed at Spotify. Custom command line interface tools can aggregate actions across multiple delivery platforms into a single subcommand. APIs can be built to define the functions of a developer platform. The APIs can support the command line interface, developer portal, and automation use cases for requirements like provisioning and reporting. Application configuration is typically a declarative representation of an application, including its code, infrastructure, and all other metadata used by the developer platform to manage the delivery lifecycle of an application. These are typically files maintained in an application repository alongside the application code. The open-source option for this is Score, which supports platform-agnostic declarative representations of applications in a YAML format. Role-based access control is supported by the developer portal, the CLI, and the APIs of a developer platform. Read and write-level access controls options ensure that only the appropriate roles are permitted to define, deploy, and modify application definitions and administer the developer platform itself. The next major component type covers the software delivery portions of a developer platform. This includes such systems as enterprise JIT repositories, CI/CD platforms, container image registries. Infrastructure's code is used to provision infrastructure required by an application and platform orchestrators. Most of these are platforms that integrate code, automate testing processes, and deploy workloads and infrastructure. The platform orchestrator executes declarative application configuration definitions, deploying the components and code defined in a configuration. Monitoring and logging is another major component type, and security is another. These component types include log collection and analysis tools, dashboards such as Grafana and Prometheus, secrets management, container security scanners, and static code analysis. The resources that are provisioned by a platform orchestrator as part of an application configuration include compute, including infrastructure as a service and managed Kubernetes, databases, networking, messaging services like Kafka or ActiveMQ, and managed cloud services. From the developer's perspective, these resources are managed by the developer platform. Changes to the application configuration that define an application are executed by the platform orchestrator. This is similar to the way a change to a Kubernetes manifest causes container pods to be instantiated or destroyed. This gives you a high-level overview of the major components of a developer platform and how they integrate. Together, these components present a much simplified surface area for developers. Instead of having to interact with 5, 10, or 15 different platforms, developers can interact with a single unified platform that enables end-to-end software delivery capabilities. Developer platform experience. I've talked a lot about internal developer platforms so far in somewhat abstract terms. Now, I'll get into specifics of the developer platform experience. What does it actually feel like to use a developer platform? I'm going to demonstrate that through a story. There's a benefit of internal developer platforms I haven't mentioned yet. New developer onboarding. Let's follow Josie and Greta. Josie is a new developer at Acme Corp, and Greta is the tech lead of her new team. Greta will be Josie's onboarding mentor, which means she'll be walking Josie through the use of Acme Corp's internal developer platform. Josie's never used an IDP before, so Greta breaks it down for her. So this IDP is your starting point for any new project. It will help you define a new application, configure it, and deploy a new development environment. And let's just take a tour through the provisioning experience. Suppose you want to create an HTTP API project that connects to a database. Your first step is to log into the IDP and define a new application. Now the IDP is going to present you with a set of options. What's your favorite development stack? Well, I'm a Java developer mostly, but I see a whole bunch of options here. How about we try Python? Okay, sounds good. We have a lot of Python devs here, so Python is supported, as well as Node.js and Java among others. Okay, select API for the type and click Next. Now you need a database. Which one looks good? I'm a Postgres gal, so let's go with that. Okay, add that to the configuration. Now you can pick your authentication method. We have auth service accounts, but let's do a static API key just for this demo to make it quick. Standard logging is captured by default, so you'll have a new logging bucket after deployment. Looking good. Now hit provision and deploy. Wow, I can't believe how easy this is. At my last job, we had to do all of this by hand. It took us a while to get here and it's been quite a journey, but now that we have it, I can't imagine working any other way. So check your email. You should have a notification that your environment is being provisioned. Okay, got it. Now what? Well, now we go get a coffee. Your environment will take about 15 minutes to provision and deploy, and by the time we get back, you should have another email from the IDP with a link to your new code repository. And that will be the code that was deployed to your dev environment. You can clone that repo and get started adding code right away. Now the important question is, do you like hazelnut coffee or vanilla? This demo showcased how a developer platform simplifies Josie's job by providing her with a single unified tool, the developer platform. This is what platform engineering means by self-service and golden paths. The self-service feature of this developer platform allowed Josie to provision a new developer environment for herself on demand. The application configuration feature provided Josie with a menu of pre-built components based on golden paths established by the platform engineering team. These components can not only be deployed but configured to work out of the box. Josie's new API project will be pre-wired to the database she chose, with that code available to her in the new repository. These are the golden pounds in action. The pre-built components provided by the IDP implement best practices across all the supporting non-functional elements of an application. Josie's used to doing all these things painstakingly by hand. Using the internal developer platform, here's what she didn't have to think about. Who do I call to get a new development environment? How do I create a new code repository? What software components are approved for use at Acme Corp? I'm brand new here, I have no idea. How do I secure this API? Where's the documentation for that? Python isn't my usual language. Which Postgres driver should I use? That's the power of platform engineering. As Josie settles into her new role, she'll continue to use the IDP developer portal to look up applications she'll be working on and reference documentation for the pre-built components. As she gets to work on new and existing apps, she'll use the developer platform CLI as a part of her code test deploy developer loop, so she doesn't have to keep going back to the portal UI. Josie will also work with the API to produce some reporting for business stakeholders. As she gets more and more familiar with the delivery process, she'll join the internal developer platform user group and provide feedback to the platform engineering team on how to improve the developer experience. Developer platform in action. So far, we've covered the major architectural components of a developer platform, and we've seen a demo on the user experience. Let's turn the clock face around and watch what happens inside a developer platform as a developer like Joe uses it. The first thing Joe did was to give his new application a name. In the background, the developer platform created an application configuration for his app in a structured format. This can be done with a commercial product or an open-source workload definition format like Score. Next, Joe selected a number of templates from the developer portal and added them to the configuration. Each component has its own internal configuration. Joe accepted the defaults and then hit provision and deploy. This is where the action starts. The process that runs from this point is similar to a CI/CD pipeline, but broader. It runs across several of the component platforms of the developer platform. The provisioning process centers on the application definition Joe created by completing the application definition in the portal. When Joe hits the button, the platform orchestrator spins up and reads the saved configuration. It's then up to the platform orchestrator to execute the steps defined in the configuration. Each template will have its own deployment configuration. For example, the Python API template might offer a few deployment options such as serverless functions, a managed container platform, or a dedicated Kubernetes cluster. Let's assume the serverless option is the default. In that case, the Python code would be deployed to a new serverless cloud function. Newly deployed functions need to be able to connect to any of the available databases. So for example, if there are 6 language stacks available and 3 databases, that's 18 possible combinations. Ideally, the database connection should be set up in the deployed code automatically, without Joe having to write it himself. There are a number of ways to accomplish this. One would be to write the database code using an adapter pattern. The templates would include one adapter for each combination of language and database, and each adapter would be defined in a separate code file. The deployment process would select the correct adapter based on the selected database. An alternative to this would be to use dynamic code generation. The selected database code could be injected into the function as it's deployed. This is a more sophisticated approach that would be more suited to advanced use cases. Joe's configuration also called for a Postgres database. Once again, the template could offer a choice between a shared Postgres instance or deploying a new one. The cost-saving default would be to use a shared platform. So in this case, when Joe accepted the default, a new schema was provisioned in a shared developer environment Postgres database. The last element Joe defined was the security option for his API project. He selected an API key. This is a secret. So the next thing the platform orchestrator needs to do is to create a new key and save it in a secrets management system. Secrets management systems are common among cloud services, and there are third-party commercial options as well. They typically support both generating and storing new secrets. The platform orchestrator in this case would send an API request for a new secret from the ICME Corp standard secrets management system. API security for new workloads will likely be handled by an API gateway. The final step would be for the orchestrator to register the new API with the gateway including a reference to the API key secret. So we can see there's a lot going on behind the scenes in a developer platform. The deployment process looks a lot like a typical CI/CD pipeline, but it's much more than just an application deployment. The developer platform is dynamically provisioning infrastructure, generating code, and deploying that code to a new environment, all with the click of a single button. At this point, Joe's new API is deployed and is set up to talk to the database he chose. His Postgres schema is ready, and the API has been secured. Success. The last thing the orchestrator does at this point is to create a new source control repository for Joe and add the code that was configured specifically for his app. The developer platform then sends Joe an email with the summary of the deployment, including the public URI of his new API and a link to his new repository. Time to get coding. Developer platform planning and design. We've now seen a developer platform from two perspectives: the users of the platform, that being the application developers, and the builders of the platform, that being the platform engineers. Now it's time to imagine planning and designing your own. The very first thing a brand new platform engineering team should do is a work planning cycle. This will then lead to a cycle of design work. This is not a linear process. Expect a few iterations back and forth between planning and design before your platform engineers are ready to really start building. It's important to strike a balance at the earliest stages between planning and execution. Don't fall into analysis paralysis. Your MVP should be, as the M stands for, minimal. The team should always be asking, how will this feature directly drive improvement in the target metrics? Let's dig deeper into both planning and design processes. The first development planning should draft a roadmap that outlines the progression from the MVP through the early production rollouts. You'll be learning a lot as your team iterates between planning, design, and development, so don't project too far into the future. Here's an example of a roadmap. The first phase might be called a pilot or proof of concept. This can be broken down into milestones aligned across developer platform components like APIs and the CLA. Include interactions with the pilot app development teams, break the development down into work streams, show the workstream dependencies so the platform engineering team can work in parallel as much as possible, and include tentative plans for scaling and productionizing the developer platform post-MVP. During the planning phases, your team will be talking about requirements coming from within the team and requests from developers. Be ruthless in keeping the scope tight, but don't throw anything out either. Keep a backlog of features outside the MVP scope so your team can pivot to more advanced features immediately after the MVP is finished. Speaking of finished, one of the agile techniques you'll want to use is the definition of done. This will be useful both at the task level and in the broader sense. When is the MVP complete? There's no hard and fast answer to this. Your platform engineering team will need to work with all stakeholders, and especially the app developers, to agree on the MVP scope. A formula for a scope might look like this. The MVP is complete when these metrics have been measured across these workloads after having been used by these teams for this time frame. This formula can provide your platform engineering team with a time-boxed set of measurable goals to achieve. Plug in the metrics you want to track, the first workloads to be built and deployed with the developer platform, the app development teams in the pilot, and the duration of the pilot, and you have an MVP scope. The design phase will bring up questions. What should we build? Which components should be prioritized? Should we build on open source or use commercial products? Refer back to the developer platform reference architectures for what can be built. You can then use research on internal practices, areas of waste, opportunities for automation to decide which components to build first. Use your high-impact metrics to build a Franklin list of features. Which features will deliver the most value for the least effort? Here's a suggestion for teams that are just starting out. Developer portals are wonderful, but they're a lot of work. My suggestion is to think of portals as a later phase effort. Prototypes and MVPs should focus on command line tooling first. Once you've decided what to build, you'll need to figure out how to build it. There are two general options: build it yourself with open source or purchase commercial software. The question of open source versus commercial can be challenging. It is possible to build a developer platform 100% open source, but that's a heavy lift. My recommendation is to strike a balance. Open source components are valuable in that they offer a low-risk, free way to learn about the components of a developer platform. You may find that some are perfectly suited to your needs. On the other hand, there may be some areas where the commercial product makes sense from an ROI perspective. So if you have the budget, invest in commercial software strategically and use open source where it makes the most sense. Designing and building a developer platform will require a significant degree of creativity. There are no shrink-wrapped just-add-compute developer platforms. They are unique by necessity. No two complex enterprises are similar enough to use the same single platform. There are, however, certainly common components that can be used to build them. Beyond that, look to other similar systems for inspiration. Remember that cloud hypercasers are in part developer platforms. Look at how they enable developers to use their services. Study CI/CD pipelines to get ideas about how to automate multiple steps across multiple platforms with a single tool. Kubernetes uses concepts that may be useful, such as declarative workload definitions. So the planning and design of a developer platform is critically important to a successful implementation. Let's move on. Building a developer platform MVP. Starting from a blank page is challenging, whether you're writing a novel or a design specification. It's helpful to start with a framework for what is possible and use that as a straw man. Let's apply this idea to the beginning of your developer platform journey. If we refer to the developer platform architecture, we see a few options for what we can build: developer portals, workload definitions, command line tools, and delivery platforms, such as version control and CI/CD systems. Where to start? I gave you a preview earlier of where not to start developer portals. Developer portals, such as the one in the demo with Joe and Greta, are very powerful, but they're not a good starting point for a developer platform MVP. Portals require a lot of time to configure and adapt to your needs. We can get a lot of benefit from simpler, more focused work first. So a minimally viable product should be just enough to move the needle for critical metrics. We can use the software delivery lifecycle as a framework for where to start. This workload lifecycle diagram shows how workloads are created, developed, and managed throughout their lifetime. The context in which these things happen is important. A software consultancy is going to need different things from a developer platform than a financial institution or a retail operation. Let's use those examples as case studies. We'll use Acme Engineering, Acme Bank, and Acme Shoes and Stuff as our guinea pigs. Acme Software Engineering is a medium-sized software engineering consultancy. They work with small to medium-sized businesses on a wide range of development efforts, including bespoke websites and application development. Much of Acme's waste in their process is in the beginning stages of the workload lifecycle. New workloads are created on a near daily basis. Much of the ramp-up time with new clients is spent on the infrastructure provisioning and version control setup. So the workload creation process is the source of the most difficulty, and is therefore where most of the opportunity lies. The platform engineering team targets workload creation for automation. They decide to include in their MVP a workload definition. Workload definitions will allow developers to quickly define new workloads in a structured, executable format, such as score and golden path templates. Golden path templates will reduce the time developers spend on writing boilerplate starter code and provisioning infrastructure. Given these requirements, the platform engineering team builds two major developer platform components: a command line tool that works directly with a platform orchestrator to provision workloads, and a small set of very commonly used golden path templates. Like all financial institutions, Acme Bank is concerned about data security. Secrets management and role-based access have been a challenge for them. There are no standards for secrets generation or storage. Developers have access to all workloads, and elevated access to higher-level environments where only operators should have break-the-glass access. The platform engineering team decides to build their developer platform around automation for secrets management and role-based access. They develop a command line tool that automates secret storage and generation, and integrate it with the LDAP system. The CLI is integrated with the company LDAP system so that the identity of the user is communicated to integrated systems, like secrets management. This serves to enforce role-based access rules implemented in integrated systems. Acme Shoes and Stuff is a large retail outlet with thousands of stores. They maintain typical retail systems like point of sale, logistics for shipping and inventory management, and back-office systems. This company's greatest struggles are related to the lack of CI/CD pipelines and observability. The pipelines that do exist are unreliable. Production incidents are difficult to detect and manage due to inconsistent implementation of their observability platform across workloads. The platform engineering team builds a command line tool that automatically provisions a new CI/CD pipeline and observability dashboards for existing workloads. You've probably noticed a common theme across all these use cases. I recommend a custom command line tool. CLIs offer a number of benefits as an entry point for a new developer platform. There are templates in every language to quickly get started developing a CLI. Iterating and development of a CLI is fast because it's 100% local, nothing to deploy during testing. A custom CLI can be extended with subcommands to cover a wide range of features. And adding new subcommands is relatively quick and easy. CLI are a great proving ground for new features. As the platform matures, these features can be moved to APIs, where they can support developer portals, CLIs, and automation use cases. So we can see that the first features developed by a platform engineering team will depend on the needs of their development teams. It's best to start small, with a simple feature set pointed directly at saving developers time. This can lead to measurable change in the most important metrics across all workloads: lead time, change failure rate, and mean time to recovery. Developer platform components. No two developer platforms will be exactly alike. However, they do have common components. Now, I'll go into deeper detail on developer portals, application configuration, platform orchestrators, and command line tools. Developer portals are typically web applications with a user interface. Many of the features of developer platforms are exposed by a portal, golden templates, software catalogs, and automations. One of the best-known open-source developer portals is a product called Backstage, originally developed at Spotify. Keep in mind that Backstage and other open source portals are not complete portals, they're portal development kits. They require a fair amount of customization to be useful. This is why I recommend holding off on portal development until after you have some success in providing more essential features. Don't get me wrong though, I don't want to put you off portals. They're very powerful tools as we saw in the demo video. I recommend studying the architecture and getting started documentation of Backstage and other portals to get ideas for the overall architecture of your developer platform. Declarative configuration has become a common standard in DevOps engineering. There are several platforms like Kubernetes that use declarative configuration in YAML files to describe what should be provisioned and configured without any indication as to how that state should be achieved. Kubernetes uses this technique to allow developers to state what containers they want running in a YAML manifest. The Kubernetes control plane handles the details on how to make it happen. The same technique can be applied more broadly to all kinds of other platforms. Open source and commercial developer platform systems use platform orchestrators to go beyond containers in a cluster to almost any configuration in any platform that provides an API. If you've watched the demo video with Joe and Greta, you've seen an example of how a single declarative configuration can execute provisioning and deployment across compute, databases, version control systems, secrets management, and more. There are two open-source application configuration systems. SCORE is a standalone declarative workload specification system. It uses a schema similar to Kubernetes manifests to specify configurations across a number of included platforms. SCORE can also be extended to cover other platforms. Kratix is an open-source platform for developer platforms. It includes its own workload configuration definition schema. Just as application configuration and declarative specifications have a parallel with Kubernetes manifests, platform orchestrators are similar to the Kubernetes control plane. The job of a platform orchestrator is to read a workload specification, such as SCORE, and then execute the steps defined in each resource type to configure them. Kratix, which runs on Kubernetes, uses the concept of promises to deploy and configure various component platforms. Other commercial orchestrators use proprietary workload specifications or open-source specifications such as SCORE. A complete tutorial on CLI development is beyond the scope of this video, but we can take a look at an example of how a CLI tool can quickly encapsulate a range of functions. Let's use the example from Acme Bank. Developers are able to use the CLI to generate secrets and store them for applications. Let's suppose our CLI is called IDP. We could have a subcommand that lists workloads, IDP workload list. We could then have a subcommand that lists secrets, IDP workloads secrets list. This command could read the workload spec without having to connect to the secrets management system. We can see how convenient it is. A developer can get this information from the CLI quickly without having to poke around in a user interface. Now we can implement a secrets reading system. Remember that the Acme Bank CLI is integrated with their LDAP directory, so the developer won't see any secrets they don't have privileges to access. This command might look like IDP workload secrets display, and then a secret ID. Quick tip, if you do implement a feature like this, be sure to configure that subcommand not to store the output in the command history. There are many other secrets-related subcommands you could add for adding new secrets, deprecating and deleting secrets. Your imagination is the limit. When building a CLI, there are many great open-source libraries available in every language to help you get started. So these are the core features you'll want to consider when building your developer platform. There's plenty of free and commercial resources out there to help you get started. Platformengineering.org and internaldeveloperplatform.org both have excellent resources. Beyond MVP scaling developer platforms. After some time in development, your platform engineering team and development teams will agree that your developer platform has reached critical mass. Many, if not all, teams are using it for at least one of their workloads. Now it's time to plan for the next phase. The minimally viable stage of your developer platform is just the first chapter of your platform engineering journey. The scope of your MVP may shift somewhat during development. However, it's important to identify a clear milestone. Plan a flag that says MVP complete. That way, all stakeholders understand and agree that you've entered the next chapter, scale. The more successful your MVP, the more application development teams will be clamoring for their favorite backlogged features to be included in the next release. The work will shift from minimally viable to most valuable. What's the next highest impact work you can do? It may be tempting to jump in and start furiously adding new features. However, that may not be the best way to scale at this point. Your developer platform pilot will likely have included only a few workloads and only a handful of developer teams. Before you start adding more features, you'll want to drive adoption across application development teams and their workloads as broadly as possible. No matter how great a new tool may be, adding tools to developers' existing workflows creates friction for them. Your MVP will only cover a few small parts of the development lifecycle, so it's likely that not every team will be excited about using it yet. Some may simply not have any use for it at all at this stage, and that's okay. This is an opportunity for the platform engineering team to take its developer platform on the road. Do workshops with application development teams. Show them the MVP feature set. Ask questions. How can we extend this platform to your most time-consuming tasks? Demo existing features and talk about how the same techniques can be applied to any stage of the delivery lifecycle. So you're in a position to scale in two directions: workloads and lifecycle automation features. Your roadshow will hopefully drive adoption of the features you've already built. Your surveys and outreach will gather a whole new set of requirements and feature requests. Time to get back to work. The next priority is to identify common requests across development teams. Any areas of waste that impact most or all teams will drive value at scale, so of course, that's your low-hanging fruit. Each new feature will need to go through the usual development cycle: prototype, pilot, and release. After a few iterations, your platform engineering team will hit its stride and begin scaling in both directions at once: new features and wider adoption. New features will drive adoption as the feature set grows to cover more and more use cases. Eventually, most or all of your application development teams will be using the developer platform to simplify their work and focus on development rather than on deployment and lifecycle management. As it matures, a platform engineering team will grow and begin to specialize. Areas of specialization will include CLI development, developer portals, automation APIs, platform integration, and golden path templates. By the way, here's a tip for building any product dogfooding. Use your developer platform to build your developer platform. Your platform engineering team can be its own first customer. Automate the process of building the developer platform itself and get first-hand experience with what works. So you want to be a platform engineer? We've learned a lot about platform engineering so far. At this point, you may be wondering what it takes to become a platform engineer, or you may be in an engineering leadership role and looking to build a team. Either way, you'll need to know what it takes to hire or be hired as a platform engineer. A Google Trends search shows that the topic of platform engineering started tracking in June of 2024, so we're on the bleeding edge. Remember, however, that Gartner expects this space to expand rapidly over the next few years. There are opportunities and challenges when riding a new wave. The idea of building internal developer platforms hasn't spread into job descriptions and postings quite yet. If you search for platform engineering job posts, you'll find plenty of hits, but the job descriptions I'm seeing now refer mostly to narrowly scoped roles targeting specific individual platforms. So if you want to join a platform engineering team, there are a few things you can do. First, let's talk about skills. If you're already a DevOps engineer, or even better, a site reliability engineer, you're ahead of the game. If you're an experienced software engineering with interests in DevOps and SRE, that's also an advantage. All of these established roles bring critical skills to the table. DevOps engineers will have automation, integration, and software delivery platform experience, such as with source control and CI/CD platforms. SRE and software engineers bring experience with both programming and software delivery. These are not the only roles in platform engineering. If you have a background in product management, that's critical as well. I've also mentioned that architects at the application, solution, and enterprise scopes can make important contributions. If you're starting off in IT, but not in any of the roles I've mentioned, no worries. You can start this journey today. One great resource I've discovered recently is the site called Developer Roadmaps at roadmap.yeshec. The DevOps Roadmap is an excellent starting point. It contains a complete track for developing the skills that can be applied to DevOps and SRE. These skills will map directly to platform engineering as well. Now, let's talk about how to join a team. At this stage in the evolution of platform engineering, the best option may be to start where you are at your current job. Advocate for the benefits of platform engineering in general and internal developer platforms in particular. Enterprises of all sizes can benefit from a developer platform. Large, complex organizations may need a relatively large team and sophisticated developer platform with lots of features. Smaller organizations may only need a simple pared-down developer platform, maybe just a CLI and some templates. You can use resources like platformengineering.org and internaldeveloperplatform.org to start conversations about how developer platforms might be useful to your enterprise. Another possibility at this stage could be to start a platform engineering meetup or bring the topic to existing meetups in your area. By the time you finish this video, you'll know enough to present an introduction to the topic yourself. Connect with other DevOps and SRE practitioners in person and online. The more people are talking about platform engineering, the faster the idea will spread. I hope you've enjoyed taking this course as much as I've enjoyed developing it. I always learn a lot when producing a new video, and it's a lot of fun to share those learnings. In this video, we learned about how DevOps shifted more and more complexity to developers, eventually leading to overwork and burnout. The pendulum needs to swing back to the middle, to a more sustainable distribution of labor among IT teams. Hence, platform engineering. Platform engineering is a practice and methodology in which a dedicated team works to combine all the complex software delivery and infrastructure platforms into one, the internal developer platform, and IDP wraps and abstracts. All the complexity of the platforms used to develop and deploy software, such as CI/CD, source control, and the compute and data platforms on which applications are run. Developers no longer have to deal with 5, 10, or 20 different platforms. The IDP presents a single experience to simplify them all. We talked about the benefits of platform engineering and of IDPs. We dove into the architecture of IDPs and how to build one from the open source and commercial options available. Platform engineering borrows and expands on existing DevOps practices. The goal is to make measurable improvements to DevOps metrics, such as lead time change, failure rate, and mean time to recovery. Site reliability engineering is also closely related both in its goals and in the skills required. I recommend referring to platformengineering.org and internaldeveloperplatform.org for resources to start your own platform engineering practice. Please feel free to ask questions in the comments section of this video. I'm wishing you all the best in your platform engineering journey.